Hi all, welcome to another video of PYQ discussion from the chapter Moving Charges and Magnetism. And in this video, we are going to discuss 2 and 3 mark questions from this chapter for the last 2 years in all the sets. Okay, so let's move on to the questions. We have a question given. An alpha particle is projected with a velocity v 3 into 10 raised to 5 meter per second I cap. Velocity is given in the vector form. Yes. Into a region in which magnetic field B is 0.4 Tesla I cap plus 0.3 Tesla J cap. Yes. So both velocity and magnetic field are given in the vector form. Yes. Calculate the acceleration of the particle in the region. You're asked to calculate the acceleration of the particle. Right. I, J, K are the unit vectors and x along x and y axis. We know that already. Charge to mass ratio of alpha particle is also given, that is 4.8 into 10 raised to 7 coulomb per kilogram. Yes. So you are given Q by M ratio, charge to mass ratio of alpha particle. See, that is given as 4.8 into 10 raised to 7 coulomb per kilogram. Right. So that value is given. Now velocity and magnetic field, V and B. See, we know force acting on a particular charge, moving charge, F is equal to Q into V cross B. This is the equation. Magnetic Lorentz force. F is equal to Q into V cross B. We are asked to find out the acceleration acting on the particle. We know how to relate, acceleration and the force. We know it is M into A. So M into A is going to be Q into V cross B, right? That is the equation we have. So then acceleration from this, we can find out A is equal to Q divided by M into velocity vector cross magnetic field vector. That is why Q by M ratio is given. Okay, so we can use that Q by M ratio here. Before that, we have to find out what is V cross B. So velocity vector cross magnetic field vector. See, we know if you go for the determinant operator here, I, J, K, velocity vector has only one component, which is 3 into 10 raised to 5. Okay, 3 into 10 raised to 5, only I component there. But magnetic field, see the rest are 0. Magnetic field B, we have I and J components. I component is 0.4, right? And J component is going to be 0.3 and 0, right? Yes, so this is what V cross B. Velocity vector cross the magnetic field vector. Okay, so now look at this, only I component will remain, See, if you go for I, these two will be 0, right? If you go for J, then again this will be 0 and only K components remains here. Look at this, 3 into 0.3. We can say 0 I cap plus 0 J cap, right? I cap part is 0, J cap part is going to be 0 only, and K cap is going to be 0.3 into 0.3 into 3 into 10 raised to 5. K cap. So finally, V cross B, we got 0.9 into 10 raised to 5 K cap. That is V cross B part, right? And that value you can use here. What is the equation for acceleration now? Q by M. Q by M is already given 4.8 into 10 raised to 7 into 10 raised to 7 into what is the value of V cross B? V cross B is going to be 0.9 into 10 raised to 5. So we have 4.8 into 0.9 into 10 raised to 12. Correct? So it's going to be some 4.32 into 10 raised to 12 meter per second square. That is going to be the acceleration of the particle. Okay? Yes. So a question from the Lorentz force equation. Fine. Next one. An electron is revolving around the nucleus in a circular orbit with a speed of 10 raised to 7 meter per second. Okay, electron revolves in an orbit. Fine. If the radius of the orbit is 10 raised to minus 10 meter, find the current constituted by the revolving electron. Electron revolve in an orbit is considered to be like an electrical circuit like that. See, we have an electron revolving in an orbit E. We know current in a circuit can be calculated as the charge flowing per unit time. And if electron revolves in an orbit, we can say charge is given as charge of electron, we know, right? That's going to be E. And time taken by the electron to complete one revolution to close the circuit is called the time period of revolution. So current in the circuit is going to be Q by T, which is actually for an electron in an orbit, it will be E by T, and capital T stands for the time period. Suppose R is the radius of this orbit. Then we know the distance, total distance traveled in one revolution will be 2 pi r, correct? Suppose that is traveling with the speed, the speed of revolution is v, then total distance traveled by the velocity or the speed is calculated as, that ratio is called the time period. Time taken to complete one revolution is equal to distance traveled in one revolution divided by speed of revolution. So that is time period. If we substitute that value here, we get E divided by, what is time period equation? I told you, time taken for one complete revolution, right? So that is going to be distance in one revolution by speed of revolution. So 2 pi r divided by v, so which is going to be EV divided by 2 pi r. And you're given all the values here. See, just substitute and simplify. We can find out, see, I is going to be equal to, E is 1.6 into 10 raised to minus 19 coulomb, right? Charge of electron, into velocity of revolution, speed of revolution is given, 10 raised to 7. See, 10 raised to 7 meter per second divided by 2 into, right, 22 by 7 or 3.14 into R. What is R? Radius of the orbit is 10 into 10 raised to minus, just 10 raised to minus 10, 1 angstrom, right? That is a value given. See, if you simplify this, you will get 0.8 divided by 3.14 into, see, what are the powers? We get 10 raised to minus 19 into 10 raised to plus 17, correct? So you will get some 10 raised to minus 2 ampere, which we can just round off into 10 raised to minus 3. So some milliampere will be the value. See, if you take this, simplify this, you will get the final answer. Okay, right. Next one. Now, two long parallel straight wires A and B are 2.5 centimeters apart in air. They carry 5 ampere and 2.5 ampere currents respectively in opposite direction. Calculate the magnitude of the force exerted by the wire on a 10 centimeter length of the wire B. So we have two wires, force between parallel conductors. That's the concept, right? Force between two parallel conductors. Both of them carry a current, we know, opposite direction. So I1 is in this direction, then I2 will be in the opposite direction as per the question. Now, distance between the two are 2.5 centimeters apart. See, 2.5 centimeters apart. Okay, this is the distance between the two. And what else is given? What are the values of current? I1 is 5 ampere supposed to be. Then I2 is 2.5 ampere. These are the current in the conductors respectively in A and B. Suppose this is the wire A and this is wire B. All right. So what was the equation? To find out force between parallel wires. Parallel wires carrying current, they have a force between them like mu naught I1 I2 divided by 2 pi r into the length of the conductor over which we calculate the force. If it is force per unit length, we know we have to take this L to the LHS, so it will be mu naught I1 I2 by 2 pi r. But the question is to calculate specifically on a particular length of wire, so that L also to be considered. See, let us just find those values given in the question. See, I1 is given as 5 ampere, right? Yes. I2 is given as 2.5 ampere, right? Then distance between the two wires, R. This distance is R, right? 2.5 centimeters. So 2.5 into 10 raised to minus 2 meters. Then we need L also, right? Over what length we have to calculate? 10 centimeter. So length is going to be 10 into 10 raised to minus 2 meters. All values are there. Mu naught, we know it is 4 pi into 10 raised to minus 7. So force is equal to, let us calculate the force. F is equal to mu naught into, right? So let us substitute the value also, 4 pi into 10 raised to minus 7 into I1 and I2 is going to be 5 and 2.5 respectively, divided by 2 pi into R. R is going to be 2.5 into 10 raised to minus 2, right? See, this is 2.5, 10 raised to minus 2, into, multiplied by the length of the wire, which is 10 into 10 raised to minus 2. So now you can easily simplify this. Let's see. See, 10 raised to minus 2, 10 raised to minus 2 gets cancelled. This can be cancelled, 2 pi, and this can be cancelled by 2, right? So what are the remaining terms we have here? So 2 into 10 raised to minus 7 into 5 into 10, the whole divided by nothing, because everything is already cancelled here, right? So we have 2 into 5 is going to be 10 into 1 more 10 into 10 raised to minus 7. So this is going to be 10 raised to minus 5 Newton. See, that is a magnitude of the force acting on the 10 centimeter long wire B because of the parallel wire A. Okay, fine. Moving on to the next. A wire of L is in the uniform. L is in the form of a circular loop A of 1 turn. Yes, we are going to make a circular loop of 1 turn using a wire of length L. This loop is reshaped into a loop B of 3 turns. Oh yes, so we are going to make one more loop later with 3 turns. Find the ratio of magnetic fields at the center of the loop A and loop B for the same current flowing through. See, the question is based on a magnetic field at the center of a circular loop, right? Magnetic field at the center of a circular loop. As an application of Biot-Savart law, we learned the equation as B is equal to mu naught I by 2A, right? Where A is the radius of the loop. And if you have n number of turns, we have to multiply with n also, right? So let us consider the first loop, okay? For A, loop A. See, loop A is a loop of single turn. It's one single turn which has a radius A, suppose. Then what will be the radius of that particular loop? We used one single wire to make a loop, right? Circular loop. So we can say the length of the wire L is equal to 2 pi A, right? So we can say 2 pi A is equal to L, because that one wire is used to make a circular loop like this. So A is going to be L divided by 2 pi. A is L by 2 pi. Then now we can apply, we can use the equation for magnetic field. Magnetic field due to the first loop is B1. B1 is equal to mu naught I divided by 2 into A. What is the radius? See, the expression for magnetic field due at the center due to a circular loop, I told you mu naught I by 2A. That's the equation. So instead of A, we have the value of A in terms of L now. So we substitute that, L by 2 pi. So 2 gets cancelled and pi goes up. B1 is equal to mu naught I into pi divided by L. This is our first equation. Magnetic field due to the first one, loop A. Now, let's see what happens in loop B. See, question says loop B is of 3 turns. Same wire we used to make a loop of 3 turns. So definitely the radius of the loop will be lesser because the same length of the wire is available. Using that, we are going to make a turn of, like a loop of 3 turns. So definitely the radius will be less. So I'm going to consider, see, 3 loops. And at that time, this is going to be A dash. The size of the loop will be smaller, right? Because we have to make more turns. See, using the same concept, we can say 2 pi A dash is going to be L. Correct? But wait, it is not just 2 pi A dash. We have 3 such loops. So 3 into 2 pi A dash is going to be L. Correct? Yes. So we can say A dash is equal to L by 6 pi. See, A was L by 2 pi. Now here it is L by 6 pi in the second case. Okay, now we apply that magnetic field equation. We are using that magnetic field equation to find out B2. So what could be B2? B2 is going to be mu naught I divided by 2 into A dash, right? A dash. But remember, same current, right? The same current flows through in both the cases, so there is no change in I. But we have, in this case, we have 3 loops, right? 3 turns in the loop. So we have to multiply with the number of turns also. Here we had only one turn, single turn. That is why it's just multiplied with 1. If we have n number of turns, that also should be multiplied. So we can say 3 into mu naught I divided by 2 into, what is A dash? L by 6 pi, right? L by 6 pi. So we can take, see, this 2 and 3 gets cancelled. I mean, 2 and 6 get cancelled by 3. 3 comes up, so it becomes 9. 9 into mu naught I into pi divided by L. See, this is our equation number 2. Equation number 2. This is B2. Okay, the magnetic field due to the second loop, the 3 turns loop, is going to be this much. Now the question is to find the ratio of, right? Ratio of magnetic field at the center due to these 2 loops. That is simply the ratio of equation number 1 and equation number 2. See, look at this, mu naught I pi by L, mu naught I pi by L. They gets cancelled. So what is B1 by B2? Simply, B1 by B2 is going to be 1 by 9, right? That is the final answer. Okay, right. So remember to multiply with this n that we usually forget, you know. So there will be n number of turns that you have to multiply here. Okay. Next one. 2 wires of equal length are shaped in the form of a square loop and a circular loop. Both loops are suspended in a uniform magnetic field. Prove that for the same current, circular loop will experience a larger torque. See, if you watch the video of the MCQ discussion of the same chapter, we have done, there was an assertion reason question in that particular discussion, you know, based on the same concept. Torque acting on a loop of wire. Yes, so torque acting on a loop of wire, we know the equation torque is equal to mb sine theta, right? Where m is the magnetic dipole moment, b is the magnetic field strength, theta is the angle between m and b, that we know. But here we have to bring that area into the discussion. See, m, magnetic dipole moment, can be written as n into I into a into b sine theta, right? Yes, n is the number of turns, I is the current flowing through it, a is the area enclosed by that loop, right? And b is the magnetic field. See, here we are talking about only single turns, so that n is going to be 1. So we can say torque is equal to just I, A, B sine theta. Okay, so this is the equation for torque, right? So torque equation is ready here. Now look at the question. We have 2 loops, they carry the same current. For same current, so we can say current remains the same. They are kept in the same magnetic field, both circular and square loop, both of them are suspended in same magnetic field, so B is also the same, correct? Yes, and there is no change in the orientation, so even sine theta remains the same. Yes, so since these 3 are constants, same for both the cases, we can say torque depends only on what? Area of the loop. So torque is proportional to the area of the loop. That is what our conclusion from this discussion. Then you're asked to prove that for the same current, circular loop will experience larger torque. So if you want to show circular loop experience larger torque, you have to just show it has more area than the square one. Okay, because torque is proportional to area. Yes, now let us come back to that area calculation. This is our conclusion, as I told you, from this one. Then we have to show more area for circle, then more like torque also will be for circle because torque is proportional to area. Okay, now let us see. If you have a wire of length L, L is the length of the wire. I'm going to make a circular loop, right, from this. See, just like in the previous question, what we have done, you know, so this is the radius of the circular loop. So we can say 2 pi r is equal to L, or radius is equal to L by 2 pi, L by 2 pi. So that is the radius of that loop supposed to be. Then how will you find the area? We need the area to compare, no? So area is equal to pi into r square, you know, so area enclosed by the circular loop. So we can say pi into r is going to be L square by 4 pi square. One of the pi gets cancelled. We get L square by what? Just 4 pi, correct? Pi into r square becomes just L square by 4 pi. One of the pi gets cancelled. This is the area of the circular loop, okay? Circular loop. Now, the second one is a square loop. What happens when I use the same wire to make a square loop? See, if you make a square loop, you know, all 4 sides will be the same. So 1/4 of this length will be one of the sides, right? So we can say it is L by 4. This also will be L by 4. right? How will you find out the area? So it's beside square, right? So it's a square only. So area of the square loop is going to be just L by 4 the whole square, and we get L square by 16. Area of the square is L square by 16. But area of the circular loop is what? L square by 4 pi. Pi, we know it is 3.14. So 4 into 3 is going to be 12 point something, 12.56 will be the value here. L square by 12.56. Here it is L square by 16. So here denominator is greater, right? In the second case, in the square loop, denominator is greater. So from 1 and 2, if this is equation number 1 and this is equation number 2, then we can say from 1 and 2, what is your conclusion? From 1 and 2, we can say area of the circular loop is actually greater than area of the square loop, right? If so, what can you do now? Torque acting on the circular loop is greater than torque acting on the square loop, because area, torque is directly proportional to the area. So you're asked to show that torque on circular loop is more than that of the square loop, and this is proved. Okay, so this is the conclusion. So we checked the area of both the loops, and we found torque is directly proportional to the area. The one which has greater area has greater torque. That's it. Okay. Next one. Write the expression for Lorentz force on a particle of charge q moving with a velocity v in a magnetic field B. When is the magnetic field of this force maximum? Magnitude of this force is maximum. Show that no work is done by this force on the particle during the motion from point R1 to R2. Yes, magnetic Lorentz force, we know F is equal to, on a moving charge, F is equal to Q into V cross B, right? V cross B. That is the expression for the force, vector form of that equation. Q is the is a scalar quantity, charge is a scalar quantity, velocity vector cross magnetic field vector. F is equal to Q into V cross B can also be written as F is equal to QVB sine theta, correct? So this is the vector form, and this equation gives you magnitude of the force, right? This is just the magnitude. Magnitude of force is equal to QVB sine theta. Yes, so this was the first part of the question. So you're asked to write that equation. So we wrote vector form and its magnitude wise, magnitude of that particular force. Second part of the question, when is this magnitude of the force maximum? So we look at this equation, we can say whenever sine theta is maximum, force is going to be maximum, correct? Yes. So what is the condition for theta to be maximum, sine theta to be maximum? Theta should be 90 degree. So what is that angle theta actually stands for? Theta is the angle between velocity vector and magnetic field vector, we know, right? V cross B. So if you have vector A cross B, how will you find its magnitude? A, B, sine theta, right? So A cross B is AB sine theta, where theta is the angle between directions of vectors A and B. Okay, so when sine theta is maximum, force is maximum. So we can say when theta is equal to 90 degree, right? F is maximum. So what is the maximum value of the force? QVB into sine theta is 1, correct? And what is the condition for that? When velocity vector is perpendicular to the magnetic field vector, because theta is the angle between velocity vector and the magnetic field vector. So they should be mutually perpendicular to each other, then theta will be 90, force is maximum. Okay, that is the second part of the question. Now we have one more point given here, one more part of the question. Show that no work is done by this force on the particle during its motion. See, we know magnetic Lorentz force doesn't do any work on a moving charge, right? It just deviates, like, changing its direction. Work done by magnetic force on a moving charge is 0. That is why there is no change in kinetic energy and all, right? So we discussed that in that, some questions related to that in MCQ discussion of the same chapter in another video, right? So here we can say work done. How will we calculate work done by a force? Work done is going to be F into S into cos theta, right? F dot S. Theta is the angle between directions of force and displacement. And we know when we write in the vector form, F is equal to, what is F? F vector, F is equal to Q into V cross B, correct? V cross B. See, from the properties of cross product of vectors, we know if two vectors A and B, if we multiply them, cross product, vector cross product, then the resultant vector will be in a direction which is perpendicular to both A and B, which means the direction of force, right? Force is always perpendicular to the direction of velocity as per the property of cross product of vectors. See, F will be perpendicular to V, F will be perpendicular to B also. V may be perpendicular, may not be, that based on the direction of velocity and magnetic field. Whenever V and B are perpendicular, force is maximum. That we discussed already. But force will be perpendicular to velocity and force will be perpendicular to magnetic field in all the cases. If force is perpendicular to velocity, definitely force will be perpendicular to the displacement also, right? Because velocity and displacement will be in the same direction. Yes, if force is perpendicular to the displacement, what is the angle between force and displacement? 90 degree. If force and displacement are perpendicular to each other, what is theta? Theta is 90 degree. If theta is 90, what about cos theta? Cos theta is going to be 0. Therefore, work done by the magnetic Lorentz force is going to be 0. It doesn't do any work. Yes. So this is the third part of the question. So we answered all three. Okay, let's move on to the next. A long straight wire AB carries a current I. A particle, mass m and charge q, moves with a velocity v parallel to the wire at a distance d from it as shown in the figure. Obtain the expression for the force experienced by the particle and mention its directions. See, you are asked to find out what will be the force acting on this moving particle. You can see the diagram. Particle is going in the downward to the bottom of the screen. You know, this is the way how it is going, and current is going to the top of the screen. So a straight wire and a point at a distance d, you know, a particle is going in this way. So particle is going to the top, to the bottom of the screen. Just understand the directions because we have to do that in detail later. Because question is not only about magnitude, but also about direction. Force, magnitude experienced by the particle, mention its direction also. Expression for the force and, magnitude of the force and direction. Okay, we know force acting on any moving charge in a magnetic field. Magnetic Lorentz force Q V B sine theta. That is the equation, right? Okay, see, to identify theta in this equation, we should know what are the directions of velocity vector and magnetic field vector. Just in the previous question we explained that, right? Theta is the angle between directions of velocity and magnetic field vectors. Okay, so we have to find out that angle theta first of all, but there direction of velocity is already given. Direction of velocity is to the bottom of the page. It is clear in the diagram, right? What will be direction of magnetic field here at the point? See, the point where the charged particle moves, you know. So this is the point where it is moving. The current flowing through this particular wire, I, it produces a magnetic field in this region. To find out that, we use the right hand, the right hand rule, you know. So using the right hand rule, we can find out what is the direction of magnetic field at that point. Stretching the thumb along the direction of the current, right, and holding this straight conductor. So magnetic field is given by these 4 fingers, we know. So that fingers are going into the screen here. So magnetic field in this region is a cross. It is into the screen. Magnetic field into the screen, correct? Yes. And there is a cross magnetic field everywhere on the right side, correct? Because wherever you go, magnetic field is going into the screen only. Throughout on the right side of the wire. Everywhere on the, every point on the left side. So, you know, magnetic field will be a dot. Yes. So basically, this particle is passing through a magnetic field, which is a cross in this region, you know, a cross magnetic field. So magnetic field is into the screen and the particle is going to the bottom of the screen. What is the angle between the two? 90. Velocity vector, sorry, magnetic field vector and velocity vector, they are mutually perpendicular. So we identified theta as 90 degree. Therefore, force expression now reduces to just QVB because sine theta is equal to 1. Okay, right. So force is ready, like expression for force is ready. Now, here Q is Q only, like, you know, we have to just substitute that Q is given in the question. V is just velocity only, that's also given V. Okay, and B is the magnetic field, that quantity to be substituted, that will be the end of that particular calculation. So for that, what will be magnetic field? Suppose the particle is moving or it is located at a point O. What will be magnetic field at the point O? How will you calculate it? We know for a long straight conductor, magnetic field at a distance is going to be B is equal to mu naught I divided by 2 pi r, right? This is the equation. Application of Biot-Savart law, right? We discussed for a long straight conductor. So we have mu I by 2 pi r, but distance given here is not r, it is just d, right? Perpendicular distance between the from the wire to the point, so it is d. So mu naught I divided by 2 pi d is the magnetic field. Then now we can find out the force, because B also can be substituted. Force is equal to, what is the force? QB into B. So we just multiply Q and V here, that's it. So Q mu naught I divided by 2 pi d into Q into V, because QV into B is the final answer. So force equation is finally mu naught I Q into V divided by 2 pi d. Magnitude of the force. See, no numerical values given. So this is our final expression. Correct? So this is the force acting on the particle when it moves. And that is a maximum force acting on it because sin theta is equal to 1. Yes. So that's about the magnitude of the force. Now, what will be the direction of the force? As I told you before, we have to find out direction of this force also. Yes. So be ready with Fleming's left-hand rule. So we are going to apply Fleming's left-hand rule to find the force acting on the particle. See, magnetic field represented by the index finger is going into the screen because magnetic field is into the screen. It's a cross only, right? So magnetic field is into the screen. If magnetic field is into the screen, look at the velocity of the particle. See, the particle is going downwards, right? Yes, so it is going to the bottom of the screen. So if you stretch your fingers, magnetic field into and velocity to the bottom of the page, then look at the thumb. The thumb shows a direction away from the wire, right? So in this direction. So it's a repulsive force from the wire. Or we can say force is acting on the particle in a direction away from it. Away from it. So basically, this is the direction of the force, right? Force acting on the particle will be in this direction. So when the charged particle goes like this, it will be deviating because of the force acting on it. Okay, so magnitude and direction of the force acting on it, that we found out. Fine. Then, next one. A galvanometer shows full deflection. Full scale deflection for a current Ig. So that is called the galvanometer current, right? Ig for full deflection. Yes. A resistance R1. A resistance R1 is required to convert it into a voltmeter of range 0 to V. Okay. So we are going to convert galvanometer into a voltmeter. We know how to convert it, right? A galvanometer can be converted to a voltmeter by connecting a large resistance, a high resistance. High resistance into what? In series, right? High resistance in series to the galvanometer. If you convert that into an ammeter, a small resistance, a shunt resistance in parallel, right? So here we have to convert galvanometer into a voltmeter. So galvanometer is connected to a high resistance R1. Yes. When it is connected by a resistance R1, question says it is converted to a voltmeter which is able to measure up to a voltage V. That's the range of the voltmeter. Okay. When we connected another resistance R2, see, if you change this into R2, this voltmeter will be converted, this galvanometer will be converted to a voltmeter which is able to measure up to what? Up to 2V, double of it. So range changes from 0 to, V to 2V, correct? When you change the resistances R1 and R2. The question is, find the resistance of the galvanometer. You're asked to find out resistance of the galvanometer, which we denote usually by G. Correct? Okay. So we know already how to convert it. As I told you, we connect a large resistance in series to the galvanometer. So the whole device now is called a voltmeter, right? This is the voltmeter. So what is the total voltage measured by the voltmeter? V is equal to, so current flowing through this is Ig, right? Ig. So we can say Ig into G plus Ig into R. This is how we calculated. The total potential drop across the device is going to be Ig, right? Now we can find out R from it. What is Ig into R? So we take Ig into R is equal to V minus Ig into G. And this is how we found the resistance of, the large resistance to be connected. V minus Ig into G divided by Ig. So if we split that into a simple form, we can write V by Ig minus G. Correct? R is equal to, so we can say R is equal to V by Ig minus capital G. This is the equation for resistance to be connected in series to convert that into a voltmeter of range V. So now let us come to the question. When we connected a resistance R1, the range was V. In both the cases, Ig and G remains the same, right? Because it is the same galvanometer. One galvanometer will have only one full scale deflection and one resistance G. So V by Ig minus G. So V is the range of the voltmeter, that is given as V only here. So R1 is equal to V divided by Ig minus G. This is the first case, right? Equation number 1. Okay, later if I change R1 into R2, this becomes 2V Ig minus G. Okay, R2, how will you write the expression for R2? R2 is equal to, from this V, instead of V, this 2V divided by Ig, correct? Minus G. It is equation number 2. Because when we change R1 to R2, the range of the voltmeter changes to 2V. So this is V, this is 2V. Okay. Right. If so, can you tell me what could be V by Ig from first equation that you can substitute here later so that we can get expression for G in terms of R1 and R2. See, we don't have any numerical values, so we'll get an equation finally, which definitely will be in terms of R1 and R2 because those values we cannot substitute, no? Then, let us find out what is V by Ig from equation number 1. So from equation number 1, what can we do? Finding out V by Ig. It is equal to R1 plus G, right? R1 plus G. Now, if this value is substituted here, what will you get? So we have V by Ig as what? R1 plus G. So I'm just going to continue here only. R2 is equal to 2 into, instead of V by Ig, I can write R1 plus G. R1 plus G minus G. Correct? That's what we got. See, R2 is now in this form. If you open the bracket, we get R2 is equal to 2R1 plus 2G minus G. 2G minus G is going to be G only. So 2R plus G. That's what we got. R2, 2R1. Okay, R2 on the LHS. The question was to find out what is the resistance of the galvanometer, right? So we have to find out G value. Now find out G from that. Just rearrange the equation. So we get finally G is equal to, if I take G on one side, R2 minus 2R1. That is the expression for resistance of the galvanometer in this case. Okay, right, fine. So moving on to the next. Two identical circular loops P and Q, each of radius R, carrying current I, are kept in the perpendicular planes such that they have a common center O, as shown in the figure. See, circular loops, and they are with coinciding centers, kept in two different planes, two mutually perpendicular planes actually. Yes, you are asked to find out the resultant magnitude of the magnetic field and also its direction. Yes. See, we know what is the expression for magnetic field due to a loop of wire, circular loop of wire at the center. Application of Biot-Savart law, right? We derived that equation using Biot-Savart law. Mu naught I divided by 2A, where A is the radius. And if you have more number of turns, you have to multiply with n. So here we have only one turn only. So we have to find out like magnetic field for both of them. And they are identical also. Identical in the sense, identical circular loops in the sense, they have same radius. So A is equal to radius of first one is equal to radius of second one is equal to R. See, current in the first one is equal to current in the second one is also equal to I. They are equal. Correct? So what will be the magnitude of magnetic field produced by both? See, look at the equation. We have same current and same radius. The rest of the quantities in the equation are constants, right? So the conclusion is, we can say magnetic field due to the point like the loop B, loop P is mu naught I by 2R. Then magnetic field due to Q also should be what? Mu naught I by 2R. Correct? They are identical loops and they produce equal magnetic field. Okay, at the center. Now, from this we can conclude, the conclusion from this discussion, BP is equal to BQ is equal to B. Right? I am going to take BP and BQ just is equal to a value B, because we have to find out the resultant. See, to find out the resultant, if you have more than one quantity, vector quantity at a point, we have to find out the resultant of the two, right? Magnetic field is a vector quantity, it has a definite direction. So we know for the loop P, if you go for the loop P applying right hand thumb rule, see, the magnetic field is going in this direction. Magnetic field due to the loop P. Whereas magnetic field due to the loop Q, see, the current is flowing in this direction. See, it's supposed to be like this. See, it is going in this direction. So if you apply right hand thumb rule there also, magnetic field due to magnetic field due to Q is going to be BQ. So we have two magnetic fields, BP and BQ, which are, making an angle pi by 2. Theta is equal to pi by 2 between them. Then we have to find the resultant. How will you find the resultant? Resultant B, R, is going to be root of B1 square plus B2 square plus 2B1 B2 cos theta. Theta is the angle between B1 and B2. See, since theta is 90, the whole term will be cancelled. And we have B1 is equal to B2, that is equal to B, right? Magnitude wise, they are equal. So I can say BR, resultant magnetic field, is equal to root of B1 square plus B2 square becomes B square plus B square only, plus 0, because the third term will be 0, cos theta. And this is going to be root 2 times B, correct? 2B square and root 2B. Then what is resultant magnetic field finally? The magnitude of the magnetic field, root 2 times B. B is equal to any one of these, right? So we can say root 2 times mu naught I divided by what? 2R. Mu naught I by 2R. This is the expression for magnitude of the magnetic field. Now the question was about direction also. So let us find out the direction. Direction at direction of resultant magnetic field BR. Yes. Magnitude value is obtained. Now the direction. See, how will we find the resultant of these two vectors? We know resultant of these two vectors will be the diagonal of the parallelogram law of vectors, and this is the direction of BR. And we know already, if magnitude of both the vectors are equal, and the resultant will always be a bisector of the angle between the two, right? Yes. So if the total angle is 90, we can say this angle is going to be 45 degree. This also will be 45 degree. So we can say direction of BR. See, B1 is equal to B2, right? By magnitude. And theta is equal to what? Theta is equal to 90 degree. This is what we identified already. In this situation, the resultant BR makes an angle how much? 45 degree with the vectors B1 and also B2, because that resultant will be a bisector of the angle. Yes, so we get 45 degree with both B1 and B2. Okay, so these are some questions, 2 more questions we had from the last 2 years paper, and we will come with another video of 3-mark discussion from the same papers. Stay tuned. Thank you.